Hello, and welcome to Backer Breaks It Down. In this episode, we are going to explore graphs of rational functions with a focus of writing a rational function given the graph. So what have we been doing so far? So far, we've been analyzing rational functions, right? So here I have the rational function 3 times the quantity x plus 1 times the quantity of x minus 5 divided by the quantities of x plus 2 and x minus 5. So that's a rational function in its factored form. And we've been analyzing these. And we've been producing graphs. Okay. And so we've come to realize that each of the factors tells us about a property of the graph. Common factors tell us there's a whole. Anything that's on top, like the x plus 1, tells me that there's an x-intercept at -1, x plus 2, there's a vertical asymptote at -2, and so on. Okay, so now what I want us to do is I want us to go from the graph to the function. So basically, you just need to identify a few things. You should identify the horizontal asymptote. You should identify where there are x-intercepts and vertical asymptotes and if there are any holes, okay? And as you identify them, you can write them as factors in their proper locations, okay? Meaning the numerator. Factors of a numerator are going to be representing the x-intercepts of our function. Do pay attention to whether the graph is simply crossing the x-axis or if it's touching the x-axis and bouncing off. That's going to be a multiplicity of 2. In the denominator, the factors there are going to come from our vertical asymptotes. The coefficient in the numerator is going to come from our horizontal asymptote. Now, I want you to do a degree check when you do this, okay? Because if you're writing a number down in the numerator to represent your horizontal asymptote, do a degree check. Is the degree of the numerator equal to the degree of the denominator? Also keep in mind that if the horizontal asymptote is 0, do a degree check. The degree of the numerator needs to be less than the degree of the denominator, and we most likely will not write 0 in the numerator, right? Factors of both the numerator and the denominator will represent any holes in the function, okay? And the y-intercept, you can use it to check your function because they don't always give you the y-intercept, but if they do, you can use it to check and see if your function works, okay? And so after you've gone and you've identified all of these things, you can write it rational function style. So we're talking r of x is equal to a quotient. So you got your horizontal asymptote, whatever the number that is, followed by any factors x minus the x-intercept, okay? In the denominator, you'll have a factor like x minus the vertical asymptote, okay? And then if the problem, has holes, you'll have a common factor of x minus the hole in the numerator and in the denominator. So let's actually try some problems, okay? Let me get my pen ready, right? So I'm just going to write out my rational functions. So I'm using R for rational. You can use any letter you want. But I got my quotient going, okay? And I should be what's the horizontal asymptote? Well, here in number 1, I have a horizontal asymptote at y equals 1. So that means I'm going to have a 1 as the coefficient in my numerator. Next thing that I should be looking for are x-intercepts. I have an x-intercept. Ooh, that's the vertical asymptote. Sorry about that. That's my x-intercept, -9. Okay, so that means I'm going to have a factor in my numerator that's x minus -9. So for us, that means x plus 9. In the denominator, I can have factors representing my vertical asymptotes. I have a vertical asymptote here at -6. So I'm going to write a factor for that in the denominator. It's going to be x minus -6, or even better, x plus 6. There are no holes in this graph. So before I declare myself finished, what I can do is I can check myself. okay, because I do have a y-intercept. So when x is 0, y is 1.5. And so does that check out? Well, if x is 0, then on top I'll have 9. And if x is 0, on the bottom I'll have 6. And that is 1.5. So it checks out, and our function looks excellent. Like, this is totally our function. So why don't you pause this now, try number 2, and then check back in with me. Okay, so let's see how you did on problem number 2. I'm just going to get my quotient up and going. Starting with any horizontal asymptotes, which we have at y equals 2, so there is a 2 coefficient in the numerator. This function has 2 x-intercepts, one at +1 and one at -1. So there are 2 factors in my numerator. So x plus 1 represents the x-intercept at -1, and then x minus 1 represents the x-intercept at 1. And then I have 2 vertical asymptotes, one at +3, one at -3, and so I'm going to have factors, 2 of them, in the denominator, 1 for each of them. So I'm going to have x plus 3 and x minus 3. I don't know what's going on with my pen. I apologize. They don't specify any vertical intercept or any other points, so this is all we have to work with. So I guess it checks out. Why not, right? In problems 3 and 4, they verbally describe the function to us. We're just going to do the same thing. And honestly, as we read it, we can write down the factor in the proper location, So this problem starts off with vertical asymptotes. So we're talking factors of the denominator. So in the denominator, I'm going to have a factor representing the vertical asymptote at x equals 1. So that's going to look like this, x minus 1. I'm also going to have a factor for the asymptote at x equals 4, and that will be x minus 4. The next property that they describe to me is a horizontal asymptote at y equals -3. So that's going to go on top as my coefficient. And then the last thing that they give us is that it touches the x-axis at x equals 2. So this is an x-intercept, so I write x minus 2. Furthermore, it says it's touching, which means it has a multiplicity of 2. So this is everything they described, and I'm just going to do a degree check, because remember, our horizontal asymptote is at y equals -3. So is the degree of the numerator equal to the degree of the denominator? Yes, it is. Our function is perfect. And in number 4, let me get my quotient up and going. So all we have to do is write things down in their proper locations. The first item is the function has an x-intercept at 1. So in my numerator, I'm going to have a factor of x minus 1. The next item that they describe to me is a hole. It says that there's a hole in the function at x equals -2. So you know what that means. That means that there is a common factor of the numerator and the denominator, and that common factor here is x plus 2. Okay. Next, we have a vertical asymptote at x equals -5. So that's going to be in our denominator as well. And it's going to be represented by the factor x plus 5. And then lastly, we have a horizontal asymptote at y equals 2. So I've gone through the whole problem. I've written everything down in the right place. Do a degree check. Since there's a horizontal asymptote at y equals -2, is the degree of the numerator equal to the degree of the denominator? Yes, it is. Our function is good. So that's how you write a rational function given its graph or a description of its graph. In the numerator, you're going to have the horizontal asymptote as your coefficient. The factors x minus the x-intercepts for any x-intercepts. In the denominator, you'll have a factor for x minus the vertical asymptotes. And if you have any holes, you'll have a common factor of x minus the x-coordinate of the hole in both the numerator and the denominator. And that's how Becker breaks it down.